present the next presenter. So we have Roberto Nascimbene, who will give the next presentation. We read just some parts of his rich biography. He's associate professor at University School for Advanced Studies in Pavia. He also has been adjunct professor at University of Pavia since 2005, teaching shells and tanks, analysis and design, and analysis and design of steel structures. And he was the head of the Building and Infrastructure Department at EU Center in Pavia. He authored more than 100 peer-reviewed publications in international journals, national magazines, and conference proceedings, and 4 books with a topic related to shell, tank structures, existing precast structures, temporary housing, and the seismic vulnerability of existing buildings. He's a national committee member in the Technical Committee for Steel Structures and National Observer in the Technical Committee for the Robustness. And he's the member of the project team EAEE for the evolution of the Eurocode 8 Part 4 and 6, and also the member of the working group related to safety in non-structural elements. So I give the floor to Roberto, and
thank you. Thank you, Marco, for the presentation. Thank you, Rita, for the organization of the meeting, and Fabrizio for chairing the meeting. I wish to at first thank Christoph and Dimitros. This part of the Eurocode 8 has been written in, let's say, 6 hands. Is the part that really required a huge amount of time, discussion, fighting, analysis, calculation, and verification. I wanted to start saying using the same line that Christoph used for silos. Let's start from the scope. Section 6, chapter 6 of the Eurocode 8 part 4 second generation is applicable to the seismic design of tanks subdivided in using 3 main properties regarding constraints, material, and shape. When I say constraints, I mean that the document is applicable to the seismic design of on-ground, elevated, and underground tanks, embedded tanks. On-ground is further subdivided into anchored tank and unanchored tank. That means not anchored. Then subdivision due to constraint and material. The rule can be applied to steel, welded and bolted, reinforced concrete, and pre-stress, precast reinforced concrete material. It's important also to highlight that we extended also to other materials. We wrote glass fiber, reinforced plastic or polyethylene, or high density polyethylene. There's a but only the principle of the seismic analysis procedure may also be applicable. When I say only the principle, I mean that the definition of the limit state, for example, of the safety verification for materials other than steel and concrete, steel and precast concrete, are not covered by the standard. Principles means, for example, equivalent mechanical model that we will see later, and so on, but not the definition of limit state and safety verification. Constraint, material, and shape. The document is applicable to circular and rectangular cross-section. We will also have peculiar principle for horizontal cylindrical tank and spherical tank. This is more or less the general scope. Next slide is related to modeling. About modeling, the dynamic calculation model that we introduce in the code uses the classical and let's say well-established method approach, classically called equivalent mechanical model. Using the equivalent mechanical model, the evaluation for tanks under horizontal seismic action may be represented using spring models that which describes the hydrodynamic response of the impulsive rigid mass, flexible impulsive mass, and convective, and corresponding height, or better, level arms. Anyway, in any case, the dynamic model should properly consider the following elements. Let's say sloshing of the liquid at the free surface, classically called convective component. Horizontal and vertical, that's important, movement of the liquid together with the rigid tank. That means the part of the fluid that synchronously move with the tank. Impulsive, rigid component. Fluid structure, vibration of the tank and the liquid. In case of a flexible wall tank, it is called impulsive flexible component. Soil structure interaction, that is going to be shown and covered by Annex B, as Christo was saying before. Sliding and uplift of an anchored tank. This is the part related to modeling. I want to just add that steel tank with and without substructure may be analyzed assuming linear elastic behavior, and reinforced concrete and pre-stress precast reinforced concrete tank with or without substructure may be analyzed assuming linear elastic behavior. Still, according to Eurocode 3 part 1.6, and concrete according to Eurocode 2 part 1.1. Point 2 and 3 in this slide are related to nonlinear response history analysis. Point 1 define the basic method of analysis. We move from modeling to analysis. Above ground and elevated tank with or without substructure should be analyzed with the force-based approach using the calculation models defined in the previous slide, specified in the previous slide according to the equivalent mechanical model. And along this line, the dynamic effects of the convective and impulsive, rigid and flexible modes of vibration should be described by an equivalent static pressure distribution applied on the wall of the tank and the bottom of the tank. If we prefer nonlinear response history analysis, or if a response nonlinear history analysis is performed, we can use the approach according to Eurocode 3.1.6. Remember that in that part, global JMNIA is defined. That means geometrical, material, nonlinear, imperfection analysis, and all the related topic. And in case of elevated tank, the same. So remember that if nonlinear response history analysis is used, we need a damping ratio equal to 2% for bolted and welded steel tank, 5% for reinforced concrete, and 2% for pre-stress concrete. We need to model the wall and the fluid, and the 0.5% damping ratio of water or other liquid, unless otherwise determined or specified, may be adopted for the sloshing volume modes of vibration if they are going to be used. Then just a few, one slide on behavior factor. behavior factor also for tanks, not only for silos. Behavior factor also for tank are limited. Just a reminder that tank should be designed in ductility class 1. Substructure of elevated tank can be designed also in ductility class 2 and 3, but the reminder is related to the fact that QR is the behavior factor component accounting for overstrength due to the redistribution of the seismic action. QD is the behavior factor component accounting for deformation capacity and energy dissipation. But for us, QS is the behavior factor for overstrength due to other sources. 1.2 for welded and bolted steel tank, 1.5 for concrete. Important also here is the part related to the behavior factor for the vertical component. About elevated tank, we refer to Eurocode 812, that is the part related to buildings. Then just a global overview of chapter 6 that refer to the classification that I did in the first slide. First, vertical, cylindrical, and vertical rectangular. Remember that these two sections are subdivided into anchored and unanchored, vertical, cylindrical, anchored and unanchored, vertical, rectangular. Then we have horizontal, elevated, spherical, and embedded tank. Each sub-chapter refer to the Annex A, perfectly explained by Christoph before, and I see later how to, just a few minutes, how to apply the table. And all these, let's say, section are further subdivided into 5 main important part. The first one is on force, because at the beginning of the design process, we need simple rule for the evaluation of the maximum force, then pressure, if we wanted to know exactly along the wall or along the base, bottom of the tank, the distribution of the pressure, then period of vibration with or without soil structure interaction, then all the variable quantity needed for the equivalent mechanical model, impulsive, rigid, and flexible, and convective, masses and level arm height, then the maximum displacement wave height for taking into account the possibility of leakage, and some the last part of section of chapter 6 regard the superposition of all these quantity forces and pressures. In 30 minutes, it's impossible to define all these tanks. So we decided, discussing with Christoph, to focus on vertical, cylindrical, above ground tanks. Here is just a advanced numerical simulation that just show on the left side a slender tank. And on the right side, a more squat tank. Why I'm showing this part? Because it's important to notice that a careful observation of the response of the liquid that is contained in a cylindrical tank, let's say, due to a horizontal motion, a horizontal acceleration, show that the acceleration will induce in the upper part of the liquid a kind of vertical wave. This periodic variation of the height of the liquid at the opposite side, opposite wall of the tank, will induce a variation of the pressure on the wall and the bottom plate. It is more or less evident that only a part of the fluid in the upper part will participate to the sloshing, depending on the slenderness of the tank, while a lower part is synchronously moving with the rigid wall of the tank. It seems attached to the tank. So the fundamental parameter at the base of the code, the part on tank, to determine the percentage of the fluid participating in either modes is the slenderness, the ratio between the height of the fluid, not the height of the wall of the tank, and the radius. In the next slide, we will show both the analytical part and some graphical part. Here is the first slide related to the impulsive rigid support reaction. I say on the left, it's important to describe exactly what we mean for moment below and above the base. But let me start from the capital F equation, that is the maximum impulsive rigid base shear, the first equation on top, and the maximum impulsive rigid vertical reaction force that for sure comes from SR, that is the ordinate of the reduced spectrum in the horizontal direction and in the vertical direction, reduced because it has been used the behavior factor. Then there's the M capital W, that is the maximum moment, rigid impulsive moment below the base, above the base plate, is the moment at the base of the wall. And capital G is the moment below the base plate that takes into account the pressure on the bottom. The first one is used for design the wall. The second one is an overturning moment for design of anchorage or foundation. Here is the analytical expression that Christoph was before showing for the simple evaluation of these forces according to the use of a table. Here we enter in the table with the slender of the tank. I suppose here a slender coefficient of 1.5. We enter there and we can simply say that we wanted to evaluate the impulsive rigid component, coefficient CF, that corresponds to a value of 0.6861 and a participation factor of 1 for the impulsive component. We take these two values, we put it in the expression before shown, where then we have to include the total mass of the fluid and the response, the reduced ordinate of the spectrum corresponding to the impulsive rigid period of vibration. And we do exactly the same for the other coefficient related to the moment. 6861 is for the shear, for example, and 2834 is for the moment above the base plate. If we move to the convective support reaction in this slide, we simply notice that the distribution of the pressure is in the opposite side. So impulsive is 0 at the top, convective is maximum at the top, and impulsive is maximum at the base, and convective is minimum at the base. As before, FBC is the convective base shear. C and please notice the difference, because before we were using the reduced spectrum in horizontal direction. Here we have the spectral acceleration derived from the horizontal elastic response spectrum corresponding to the convective period of vibration. Please take care of that because it's important to highlight that we don't use here for sure for the fluid the behavior factor, but as before, here is shown the first anti-symmetrical modes of vibration of the first mode. All the analytical expression are based on the first mode of vibration, which is absolutely predominant compared to the other mode, as the last 30 years of scientific literature can confirm. And if we come back to the previous slide, again, at a slenderness ratio of the tank of 1.5, we have 0.31 for the coefficient of the shear, and 1.82 for the participation factor of the convective mode. Let's go ahead with the next step from forces to pressure. On the left, we have a graphical representation of the pressure exerted on the tank wall, and on the right, the corresponding equation. When a tank, in general, cylindrical or rectangular, is subjected to the action of an earthquake, we have impulsive hydrodynamic horizontal pressure, impulsive hydrodynamic vertical pressure that has a linear distribution, convective pressure, inertia pressure due to the horizontal component and the vertical component that is classically more important, evident in reinforced concrete and precast tank compared to steel tank that has a very low value of the thickness of the wall. This is for the rigid wall, and for flexible, we add an impulsive flexible horizontal component and an impulsive flexible vertical component. If we wanted to evaluate, it's clear, highlighted in the code, the pressure on the tank bottom, we can use exactly the same expression defined in this slide, using a non-dimensional, the non-dimensional vertical parameter equal to 0 that corresponded to the base of the tank. Application of the table. Here we can, on the left side, the coefficient for the convective pressure component. On the right side, the coefficient for the impulsive rigid pressure component due to the horizontal pressure component. If we enter with the slenderness as before 1.5, and we wanted to evaluate the pressure at a half of the filling level, 0.5, we have for the impulsive 0.77, and it's important to highlight that more slender is the tank, more is the component of the impulsive pressure, and we have 0.22 for the convective component. This is the two values that we have to insert in the equation as we have seen before. If we enter in this table with 0, we use the value for the evaluation of the base pressure on the bottom of the tank. This is a graphical representation on what we were representing before. On the left side is the distribution over the height of the tank filling level, the distribution of the pressure. More slender is the tank, 5 here of slenderness. More uniform is the distribution of the pressure, quite close to a rectangular Y, because more or less all the mass in the tank participate to the impulsive rigid movement. More squat is the tank, 0.5 of slenderness, less is the impulsive pressure. On the right side is the distribution of the pressure along the bottom. And you can here appreciate that more slender is the tank, more linear is the distribution on the base, and more squat is the tank, more is the non-linear distribution of the pressure. Let's move to the Annex B. Annex B, it's very important because give rules to consider the soil structure interaction effects in the calculation of cylindrical tank. If someone is going to ask, what about rectangular tank? I can say here that the impulsive rigid period for vertical and horizontal component, for flexible and rigid rectangular tank, including soil structure interaction, may be calculated, evaluating using the calculation approach for vertical cylindrical tank, replacing the radius of the cylindrical tank in the equation with the half length, capital L, half length of the rectangular tank in the seismic action, along the seismic direction. That means that you have to apply in one direction for rectangular tank and in the perpendicular direction for rectangular tank. Here, in case of rigid tank, without considering soil structure interaction, the period has to be taken equal 0. If you consider the soil structure interaction, you have to apply the two equations here written for horizontal and vertical direction, where three coefficients are used for evaluating the horizontal stiffness on homogeneous soil for the supporting condition, horizontal, rotation, and vertical coefficient, depending on some parameter that can derived according to the Poisson ratio of the soil in the table that is shown here. Convective component period of vibration. Easy for the first period. Remember that it is related to 2p and the radius. This is the reason why we can reach period of vibration of 4, 5, 6 seconds. In case of tank without a roof or with floating roof or with fixed roof, is not important because code give rule for tank with fixed and floating. The maximum vertical displacement of the liquid surface is needed. The reason why you can find it here to determine the freeboard that must be provided for checking overtopping, spillage, impact on the roof. Here is the part after the forces and the pressure is the period is the component relating to the equivalent mechanical model that we have seen before, quite close to the expression that probably many people know and comes from the US standard. We removed all the expression that we are using Besser factor of the first kind, and we use the simple expression. Here is for the impulsive rigid component for welded and steel tank cylindrical. Two parts are subdivided. The graph showed that the more slender is the tank, more is the component, 80%, 90% of the total mass contribute in the impulsive period, and more squat is the tank, less is the component of the mass. And we can also notice that the height of the level arm of the mass for the varies in a relative narrow range. The overturning height varies widely, and it is greater than 1 as expected due to the overturning moment. And in the next slide, we have the approach related to the convective mass. Again,
Roberto, it's frozen.
Yeah, maybe it's a problem with the connection. Okay.
Sorry, Roberto is frozen. I don't know.
Maybe he lost the connection.
Nós?
Yeah, let's wait a couple of minutes. He will probably return.
me ask him to reconnect.
He's disconnected, so probably he lost the internet connection, but I suppose quickly he will be back. Okay, he's back. Hi, Roberto. He's back.
Roberto?
Where?
Are you-
Apologize. I don't know what happened in the connection.
No problem, it happens.
Sorry, I start again to share the screen on the last 3-4 slide. I cannot share. You need to give me the permission.
You should allow now, Roberto. Please
Yeah,
try.
yeah, it's true. Yes, thank you, Rita. Okay. I was at the convective part of the I was concluding the convective part, saying that the convective mass is more in case of squat tank, and then I have just a few very easy slides saying that we introduce elevated tank, analyzing that using a two-coupled mass model representing the convective impulse vibration mode, including a component of the elevated staging structure, and the flexibility of the tank can be neglected. Then we, in our mandate, there's also the horizontal tank that may be more or less calculated for using an equivalent rectangular tank model, and in case the slenderness is more than 1.6, the convective pressure component and reaction may be neglected. Then it was not present in the first generation code, the spherical tank, that we introduce with well-established literature on the topic, including the first fundamental convection period, impulsive rigid vibration, and horizontal and vertical reaction forces. Then the last part is very important, is the superposition rule. Here, our decision in the second generation code was to use the square root of the sum of the square rule, SRSS rule. We completely removed the absolute maxima rule. And here you can see the first is the superposition of horizontal pressure, second vertical pressure, and the rule that already has been introduced by Christoph in his presentation, that is related to the design of structure that are axially symmetric along a vertical direction, and well defined and explained by Professor Van Vatsikos. Here is the superposition, same for the forces. Before was for pressure. Forces means base shear, vertical reaction, moment at the base of the wall, above, and moment below the base of the wall. And my last slide is only a summary that has been a part of the general comment in the first part of the presentation of Christos, is the verification of the significant damage that is going to be related to the global stability, foundation, tank shell. Please consider the problem of the buckling. You know that there's an for steel, elastoplastic buckling, classically called elephant foot buckling, and elastic buckling called diamond buckling, referred to Eurocode 3, part 1.6 and part 4.2 related to tank. Substructure, the building, let's say, the staging and anchorage system, we need to check the freeboard, as we already have said in the slide related to the maximum wave height, and please ancillary element, but this is the topic of the meters. The verification of the damage limit state and fully operational limit state. I think I reached 32 minutes, Rita. So I think I'm on time. I forgot the slide with the thank you for your attention, but I say thank you for your attention and apologize for the network.
So thank you, Roberto, for being with time with this presentation, and let's go directly to the Q&A. So I will read Pierre Wendel from Hochtief, Germany. Are any procedures included or recommended in part 4 to analyze the effect of tanks with not sufficient freeboard for the slotting wave? This question is related to the calculation of the natural frequency, but also for the resulting top pressure in closed tanks with insufficient freeboard.
Okay, thank you. Let's say we didn't explicitly include a part that make the user able to evaluate the impact on the roof for a couple of reasons. First, because you can have a flat roof, a conical roof, a spherical roof, a floating roof, and we give the possibility to evaluate the most important parameter, that is the period and the wave height, to check the freeboard, and then you can use or more advanced analysis or very simplified analysis. I suggest the simplified analysis with a linear distribution of the wave height. Linear means that you can use not 0.84 but 1 is a very safe conservative level of wave that can easily, more or less easily, make the practitioner able to evaluate the pressure on the roof or the rotation of the floating roof. Suggest to read a very good research paper from Professor Paolacci on the topic of floating roof on this field.
Okay, thank you for the answer. And next one is from Richard Albert from Germany, slide 15. What are the limitations of soil structure interaction effects on large tanks and subsoils with deep foundations?
The friend Richard classically asks this kind of not so easy answer question. Okay, soil structure interaction limitation. Probably you are referring to the I mean, not geometrical limitation. I think it's the limitation, let's say, of the validity, I can say, of the equation that are represented in the Annex B. There's also some limitation regarding the damping of the soil, for example, that were not covered in the first generation. But in that case, I suggest we follow more or less. We follow more or less the same line defined in the first chapter of the New Zealand Code for tank.
Okay, thank you. Guido Furgieri, figure A6 of Eurocode 8 part 4 shows H to L to Q0 relation for impulsive pressure on rectangular walls. In the most recent version, from 2006, H to L is on y-axis and Q0 on x-axis. In the previous version and in the reference documents, the axes are switched while graph is the same. Which is the right relation? Thank you.
This is a book, not a question, but anyway, Q0, Q0 is a nomenclature, if I remember it well, using the previous version, 1984 of the New Zealand Code for rectangular tank that has been also used in the last version of done by Professor Whittaker. I think that for rectangular tank, the most important let's say, procedure that we suggested is to refer to the cylindrical tank, as I was saying in my presentation, moving from radius to the half length, and the expression of the coefficient in Annex A. We checked with the graphical version of the New Zealand code that more or less are referring to the first mode of vibration for convective and impulsive, and all these kind of expressions are really well compared and well established. I don't think I'm not sure I answered the question, but I can answer more offline if you wanted to write something more detailed.
Okay, good. And I think the last question, then we are in time, from Carlos Arboleda. For the case of slender rectangular tanks, is the superpositional pressure component still done simplified as the absolute sum of the convective and impulsive components, which are calculated based on the pressure distribution for rectangular squat tanks?
Oh, that's a good question. I think that the answer depends on what we consider saying a slender rectangular tank. If it is really a long line, it could be that is the same like when you move from plate design to beam design, let's say, because the behavior of a very, very slender tank is like the behavior of a very, very slender cylindrical tank. Is more a tube than so. This is important because we define limit in the table of the Annex A regarding the coefficient that we can introduce in our equation, and we let's say range from 0.2 to 10, but we can really see easily that from 5 to 10, more or less, the convergence is in the asymptote, let's say. So I think that it's true what he's saying, but please be careful about the equivalent behavior of the real tank.
Okay, thank you, Roberto, for the presentation on this complex topic and also comprehensive answers.
Thank
Now,
you.
very short question.
Of course, Fabrizio.
Concerning the limit states, so what about the sliding effect concerning the above ground storage tanks and the assumption of friction level that you should consider? Because sometimes for very large storage tanks, this could be a problem, especially also in the evaluation of existing storage tanks, but also for the design one.
You are right, and this is probably a mistake of mine or the limited time, but I did not introduce a specific slide on an anchored tank. But you know that there's two big chapters in the code with a very new and advanced formulation on an anchored tank where sliding, but I also say the rotation of the bottom with the plastic hinge and meridional deformation of the are included as a part of the analytical model and the verification. Again, as you know, because you are used to do that, these are tanks that can live in our code in the safe side, but more advanced numerical model are really required to take into account this behavior for an anchored tank. This is the reason why we give the possibility for nonlinear time history analysis.
Thank you very much.
Thank you. Thank you.
Okay, so we are perfectly in time for the break. So I think it's good to take a 15-minute break for audience to refresh a little bit, and if someone from the audience has these additional questions come up to mind during the break, you can write it down, and I think the presenters will answer it in the written form. Thank you.
Thank you.
I'll come back in 15 minutes with the next presentation.